Yes, recording. So I would like to greet everybody right here in Budapest and all my participants. Our speaker today is Alex Rutar, who is going to talk about very interesting things, but written over there.
Great, thank you. Yeah, so I want to talk about a project that put a year and a half old now.
I'm sorry. I also need to say that everything is recorded. Recorded. The online part.
Okay. Yeah, so I want to talk about a project. It's about a year and a half old now. It's based on joint work with Amnon Badaji, who's also currently in Jyväskylä, although this was finished when he wasn't there. But anyway, it's a problem about infinitely generated self-similar sets. So I guess I think everyone is familiar with usual finitely generated self-similar sets. But let me kind of set up some notation. So just for concreteness, we're just going to imagine that everything is in R or something like this. But in practice, it works in RD. It actually also works for self-conformal sets and things like this. So anyway, so here's kind of the setting. So we fix some index set I. So I is some index set is finite or countable infinite. The countable index set. And then for each I and I, we have some map. It's called f of I, which is a similarity map. And which is strictly attracting. So I have some finite maps f of I and I. And associated with this data, with this collection of maps, assuming some sort of compactness condition, because there are infinitely many instead of just finitely many, there exists a maximal.
Would you write, please write with a bit bigger?
Is it too small? Okay. I can try. I don't have so much space to write so much bigger than this. Okay, so in the usual self-similar case, right, we would have some invariance relationship. There's a unique complex set K, and there's a unique over I and I. That's the I. Okay. In the infinitely generated case, such a complex set may not exist, or like such a complex set might exist, but maybe it isn't the maximum one. So the infinite case, instead of asking for a complex set, we ask for a general Borel set lambda. So there exists maximal, let's call it lambda, which satisfies the invariance relationship. So note that maybe not compact. But we won't worry about that too much. Also, if you don't have more assumptions on the maps, also maybe not Borel. But we will go with the assumptions that we will put, it will always be not, but it will always be Borel. I think that's quite shocking. Anyway, so we're into the geometry of such a set like this. So maybe a concrete example is nice. So we can imagine that our setting is the map from R to R, and we can imagine that we start with the interval 0, 1, and then we just consider maps which map this interval down to some pieces. So in the middle third Cantor set, maybe you would have 2, and instead we have lots of pieces that go like this, etc., etc. So in each f sub I is the map which takes the interval 0, 1 to this interval I, just contracts down to this. And then because of this similarity relationship, we just iterate this construction. So now again at each of these pieces, we do the exact same thing. So we start with the interval, then we map it down to all the sub-pieces. We do the same thing at every single one. So we do something at level 1, something which is potentially very complicated, but then we iterate the same construction inside each of the intervals all the way up to infinity, and then we take the intersection of all the pieces, and then the resulting set is perfect. And because this is the fractal geometry talk, at least from my okay, so there's lots of things you can ask about this set. From my perspective, the natural question to ask is to ask about like what are the dimensions of lambda. So my perspective is the following. My perspective. So what are the dimensions of of this. Yeah, so hiding under this, there are secretly some assumptions. So first of all, the first assumption I want to make is some sort of separation assumption. I'm kind of assuming that all of these maps map the integral to disjoint. So I need something like the open set condition for those who are familiar with this. So I have some assumptions, something like an open set condition assumption hiding underneath. Also, that these are similarity maps. In general, you only need conformal maps, but anyway, that's not too important. Basically, the main picture to have in your head is something like this. So these sets were first introduced in 1995. So in 1995, this formalization was introduced by Malden and Rabansky. And they were also interested in Hausdorff dimension, and they were interested in Hausdorff. So with Hausdorff dimension, you want to produce some sort of optimal cover for a set, but there are no rules about the radii which are involved in the cover. So a natural guess for a cover to take. So you want a cover for the set. So what can we use for the cover? Well, we can just take the cover which is produced from these integrals. So we can take our initial IFS, we can iterate to some large level n, and we can just use the covers which naturally occur just by taking these integrals. You just use the constructing integrals. I'll write this here. So there's a natural cover. From constructed intervals. So if we use this cover from the constructed intervals, what does that look like in terms of some sort of like cost function, in terms of like t-dimensional cost function? So we can define a function called p of t. So what is this function? So let's imagine that we take a cover existing of these intervals, and we want to know what is kind of what is the dimension of when we get this using these covers. Well, we define a function p of t, which is, well, we need to sum over all of our intervals. We want r sub I raised to the power. And here r sub I is the contraction ratio. So if this is with 1, then this is the size of this sub I, r sub I to the t. This is like the cost of the cover at level 1. And I can iterate this relationship. I can do the same thing where I sum over level 2 or level 3 or things like this, like as n goes to infinity. But because things are similarities, that's basically the same as taking this and raising this to the power n. So somehow in this case, it suffices to consider only the first level. And then what do we want? We want to know the critical threshold where this number is. We want this to be equal to 1. Maybe let me change this. I want to find a few logins. Okay. So just by using this as the cover, the following is true. So the Hausdorff dimension of lambda kind of corresponding to the covers which come from the intervals, well, it's bounded above by the following number. The beam over 0 or p of t plus 0. So if I is a finite index set, of course this is actually going to be 0 for some value of t. But because I is not finite, it could happen that this function p of t jumps from some negative value. So maybe the function is negative and then immediately jumps to being like plus infinity. So there might not actually be a 0. So writing this in this way, where we take the infimum where values where it's less than 0, is actually necessary. Yeah, so this is one slight difference from the finite case. So anyway, so this is a natural upper bound. Right? So natural upper bound comes from the geometry, comes from the construction of the set. And what Malden and Rabansky proved, theorem. Can you see the bottom of the screen from in the camera? Yeah, okay. And theorem. And then this is an equality sign. Malden from 95. Is it actually the Hausdorff dimension is actually equal to this number, okay, which is this infimum of the spread. And then let's call this an yeah. So the main work, of course, is getting a lower bound. I mean, how do you know you can be better than just using these intervals? And they do this by constructing some reasonable measures supporting the set. And I won't go into too much more detail about this. Basically, there's some sort of way to prove that this is the best possible covers. And let's call it subrogation. Okay, so Hausdorff dimension is well understood, kind of only in terms of this type of data. So what sort of information do we need to determine the Hausdorff dimension, assuming the open set condition? Well, we just need to know these numbers are divided. We just need to know like how fast is the system contracting in some sense. So after Hausdorff mentioned, what are the most commonly studied in dimension? Still two. Okay, so after Hausdorff dimension, the next thing that one would be interested in is Fock dimension. So Fox. Okay, so with Fox dimension or with Boski dimension, we now no longer care. We're no longer interested in covers of any size. We're only interested in covers of specific size. But anyway, we can forget about that. We can forget that we know this because at least in the case in the self-similar case at the Fox dimension and the Hausdorff dimension are the same in the finally generated self-similar case. So in the infinite case, one might hope because of the self-similarity that there's enough regularity that one shouldn't have to worry about that too much. But it turns out that there's also a kind of trivial obstruction somehow. So there's a new obstruction which is really weird, which only shows up in infinite case. New obstruction. Let's just look at a very, very small subset of this attractor. So instead of looking at the entire thing, let's only look at so instead of looking at the entire set, let's only look at the left end of this set. This is an infinite set, so it actually for Hausdorff dimension, this is 7 to 0. But for box dimension, I mean sequences can have positive. So the new instruction, let's call F. It just be the set of left endpoints, let's say. It's just S of I and 0 for I and I. So in the finite case, this is just a finite set, so we don't care at all. But in the infinite case, this set can have the upper box dimension, the box dimension doesn't have to exist. Say the upper box dimension of the set F could be bigger than 0. And also the upper box dimension of the set has nothing to do with what the contraction ratios are. You can imagine that you have a very, very dense sequence. B makes the R sub i's extremely tiny. Right, and then the upper box dimension of F will actually matter a lot. So F here is a subset of lambda in a set possibly with the upper box dimension bigger than 0. So this means that the upper box dimension let's say, well, of course, at least the Hausdorff dimension, and it's also at least the upper box dimension of F. So we have some lower bound, which just means that the upper box dimension doesn't necessarily have to equal positive dimension because it looks like this kind of trivial obstruction. I mean, okay, so I'm saying trivial obstruction because it looks like a very small set, but also because of self-similarity, we also need to remember that this set F also appears here as well, and here as well, and here as well. But we don't seem to consider the obstruction at level 1. This obstruction is appearing at every single interval, all the way down to the bottom of the entry. So actually, this obstruction is like quite substantial, but somehow because of the self-similarity or the self-conformality, like we only kind of witness the obstruction at level 1. But if you kind of consider the higher iterates, that they will contribute some new value. So anyway, so there's some obstruction here. So we have this Hausdorff dimension. We also have this orbit set, this fixed point set. But then again, that these are the only two obstructions. Again, it's not a theorem. Also due to Malvin and Vronsky. This time is from 1999. Is that this is an equality. So the upper box dimension lambda is equal to the maximum of H, and the upper box dimension of F. So we have the Hausdorff dimension lower bound, and then we have this weird obstruction which is coming from the 6-point set. And then other than these two things which go wrong, this kind of gives you all the information you require to understand what the upper box dimension is. Okay, so yeah, so this is 1995. The Hausdorff dimension result was 1995. The upper box dimension result is 1999. So the question that Aldo and I were interested in, I think it's very natural. So what about lower box dimension? So this is a natural question. I mean, maybe you would hope for. So like, what sort of things would one hope? So I guess the natural questions are like, okay, so is there a formula? And what sort of inputs would you like? Well, we would certainly like to take into account H. Maybe we would like to take into account the lower box dimension of M. Maybe we would like to take into account the upper box dimension of M. Okay, so is there a formula? So is there a concrete formula for the lower box dimension? Another kind of question, none of us would be much interested in is, does the box dimension always exist? Yes. Yeah, so I think we were somewhat surprised that even though these things are quite long, that no one seemed to have sat down to try to do the lower box dimension case. Okay, so this is what I want to focus on for the rest of the talk, is the lower box dimension. So there are some easy things that we can say, right, without working too hard. So the first thing is there's nothing special about this lower bound, right? I mean, this lower bound is just also holds for lower box dimension, just replace the lower box dimension here. So of course we have some lower bounds. So the lower box dimension, so the maximum of H and the lower box dimension of that. Well, this is the lower bound for the lower box dimension. Lower box dimension of lambda. And then we can also just put the upper box dimension of lambda, I guess. Because why not? And this is equal to the maximum H. So we have some lower bound and some lower bound and some upper bound.
So here F is first level set, and what if you iterate n times and denote as Fn?
Exactly. So the dimension will not change. Sorry? The dimension will be the same. Or like it might not be the same, but it'll be at most the maximum of H and the whole. So somehow, like every time you iterate, the size won't increase by more than each dimension somehow. Yeah. So it could become larger, but it won't become too much larger. Yeah, so this is why it's enough. So some of the self-similarity is what's letting you, which is why the self-similarity is why it's enough. If you only consider the first couple. Okay, anyway, so we have these, let's call them trivial upper bounds. I mean, the lower bound is literally trivial, the upper bound is trivial modulo that result, which is not. All right. So there are a few situations when the box dimension just exists. So we know the answer in a few cases. So the first case when we know the answer is when H is really big. So of course, if H is larger than the upper box dimension, then everything just collapses, right? So the reason we know that the lower box dimension of lambda is the upper box dimension lambda. If well, we have case one. H is very large, so H is larger than the upper box dimension. Okay. And then case two, of course, is when F is a nice set, when these two numbers are themselves the same. Then of course everything else collapses. Okay. So the box dimension of F exists. So the interesting thing, I'll just jump very quickly to conclusion, I guess, is that these are the only two ways for the box dimension to exist. So with here. It's just running like that. So the box dimension of lambda exists. If and only if one of these two things happens. If and only if 1 or 2 happens. So basically there are two, let's call them trivial mechanisms for the box dimension to exist. And if one of these two things does not happen, then the box dimension never exists. So these are the only two ways. So either H is just so large that the fixed point set doesn't matter. So this is like this the finite case, or the fixed point set itself is quite nice. So, and these are the two ways. And if one of these two things doesn't happen, then the box dimension does not exist. So this result actually comes from. Okay, so I kind of so what do we say with the lower box dimension? Well, can we come up with some sort of formula in terms of some numbers, or is the box dimension is okay? So we're saying that the box dimension does this, and this follows from a formula. So this follows from bounds on the lower box dimension. So why does this happen? So this follows from the following bounds on the lower box dimension. So compared to self-dimension, the lower bound is sharp. So we always have like the maximum of H on the lower box dimension. That. Well, it's lower the lower bound, the lower box dimension of lambda. But then this is bounded above by some horrifying number, which I'm going to write down. It's like h plus F over I can never remember it exactly. I wrote it down in my slide because I don't remember. Okay, I write down the formula and then I explain what all the numbers are. So T minus H, 1 minus H times S over T minus H minus S. And this formula assumes that T is bigger than H, where here T is equal to the lower box, T is equal to the upper box dimension of F, and S is equal to the lower box dimension. So this is the bound on the lower box dimension, which is kind of given in terms of all of this information. So given that we know what the Hausdorff dimension, the lower box dimension, the upper box dimension are, this gives some sort of upper and lower bound. Yeah, so I say T is equal to H because if T is less than or equal to H, then we're in case 1, in which case everything is just these two things plus. So it turns out that the reason why the box dimension does this, so this number is always strictly less than the upper box dimension. You can just check it. So this is just a computation at this point. This number is always strictly less than the upper box dimension of lambda, as long as one of these two things doesn't happen. So basically, we have some very we have some bounds in terms of the bounds are sharp, the bounds in terms of all the information, and this bound is telling you that the box dimension is not it. But this is not super insightful, right? I mean, okay, so there's this like complicated bound, and there's a T and H and S and on all this other information, but it doesn't actually tell you what the lower box dimension is. So to give you some lower bound and upper bound on the lower box dimension. And also, where does this number come from, right? Like, why would you think that this is a reasonable number? So to me, this is like, there's no good reason to think that this is like, yeah. So where's the number coming from? So that's what I want to talk about. Where is the number coming from? And like, why is it you So it turns out to answer this question. So to answer this question, So there are lots of results like this, where what we actually had to do is we have to answer a harder question. And turns out that the harder question will have an easier answer. And then we'll use the easier answer to the harder question to understand where okay, easier answer, simpler answer. The harder question is the simpler answer. And that itself will give the information that we need to get this very unintuitive pattern on the box, on the lower box.
Do you have counterexamples?
Sure.
Do you have counterexamples for regular condition 1 and 2?
Yes, it's very easy. Yeah, because the set F and the number H are totally independent. So you can basically fix your favorite sequence set, anything you want, which can basically be anything. Like any set is basically a sequence set. You can approximate any set by a subsequence set, and then just choose the contraction ratios to be extremely small. So the H is very small, and then yeah. So it's very easy to put up examples where.
And the upbound relate to sharp upbound.
Yes. So I'll talk about this example. So not only are the lower upbound sharp, every single possible value in between is possible. In the sense that, given all this information, it's possible to construct an example where you achieve the value in the middle. So it's sharp, and you can't do better than this. It's not only a function of these numbers. You need to have more information. Yeah. So this is what I want to talk about. So the lower box dimension does not only depend on the lower box dimension of H. So we're going to answer a harder question. So the lower box dimension and the upper box dimension are both special cases of. So the lower box dimension and the upper box dimension are asking for the scaling rate of the covering number. But what we can do is, instead of asking for like the rate at which the covering number scales, we can just ask, can we come up with an explicit asymptotic formula for the covering numbers themselves? So what we're going to do is, instead of asking for some sort of like limiting information, like the lim sup and the limit, we're going to ask for asymptotics of this number, n sub r of lambda, as a function of r. So we want to get higher function. We don't just want to know where it's big and what's the largest and smallest values. We want to know everything about it. So I'm going to pick a normalization, which is very convenient because it makes this function nice. So I'm going to define the function. So now here is just E is just some general subset of metric space, some bounded set. Let's say E is just some bounded set of R. E here is going to be taken many different values. So given a set E, I define the function G sub E. So what does it take value? So G sub E has an argument U, where U at least 0. U is just some positive number. Well, it's equal to the base 2 logarithm of n sub 2 to the minus u of the covering number at scale n sub 2 to the minus u of E. So I picked this normalization for a reason because it makes this function particularly. So there's lots of different things you can pick for normalization. This is one particular choice for the normalization. Right, so then of course, let's just clarify. So the upper box dimension of B is equal to the lim sup of G of U over U, and then the lower box dimension is equal to the of G of U over U. Right, so this function is encoding the upper and lower box dimension, but it's also encoding lots of other information, which is also the intermediate scaling properties. Okay. So why did I do this specifically? So why did I pick a logarithm and do this domain change? It's because it makes this into a Lipschitz function. So what are the properties? So the first property is that, well, G sub E of 0 is, okay, I'm right equal. It's basically, it's morally 0. E is some bounded set. So up to some global constant which only depends on, up to some global, this is basically like some fixed constant. So it's 0 at 0. The second property is increasing. Well, it's increasing just because it's monotone. As you get smaller, you need more balls. You need more balls to cover. The smaller your set, the smaller the scale. As you get bigger, the scale gets smaller, so you need more balls to cover the set. And the third property is that it is, okay, E is a subset of RD, of the opposite setting R, or yeah, E is a subset of R. There's also a one Lipschitz. So why is this one Lipschitz? So to understand the one Lipschitz property, we need to compare the covering number at scale 2 to the minus u plus v versus the covering number. So we need some sort of bound on the covering number, and it's 2 to the minus plus v. Well, how do we get a covering number at this scale? Well, what we can do is we can start with the covering number in terms of balls of radius of x 2 to the minus u. So we start with the covering number at scale 2 to the minus u. And then we just use some sort of trivial bound that's coming from ambient dimension. So here, our ambient dimension is 1. So we just we know nothing about our set. So we just cover each of these balls completely, just using the ambient spatial dimension. So we need like a one-dimensional family of balls in order to cover this at a smaller scale. So that means we multiply this by 2 to the v. Because 2 to the gap between the scales is 2 to the 2 to the minus v is the gap between the scales, and we need the reciprocal of that number of balls in order to cover each bigger ball. So we just take it off and we'll cover at scale 2 to the minus u, and just use some trivial bound from ambient space. And then we take a logarithm here, and we see the factor v comes out, which is the same as saying it's one Lipschitz. Okay, so we have an increasing one Lipschitz function. And if you're an RD, then it would be d Lipschitz and things like this. Sure. Okay. So so what is our new question? So in the earlier problem, we were interested in the question, okay, so can we work out what the upper or lower box dimension of lambda is in terms of this number h and some information about f? So maybe the new question is, what is, so we want to know what this function called g sub lambda of u. So we want to know the asymptotics of the covering number lambda. But of course, we're asking for way more, so we better have more input. So what is this number given, let's say, the number h and the function, let's say, g sub f. So you give me your IFS and you tell me what the Hausdorff dimension is, and you say, okay, this is what the set of fixed points is, and you say, okay, here is this kind of asymptotics of the covering number at fixed scale for the set of fixed points. Then what is the, can you tell me what the function g sub is? Okay, so again, we can just run some similar thing that we've been doing before. So the first thing is that, of course, we have that f is a contained in lambda. So since f is contained in lambda, I mean, if you replace e by something bigger, this number just goes up, right? So then f is contained in lambda. So certainly g sub lambda has to be the g sub f has to be a lower bound for g sub lambda. But it turns out, well, we can also witness the self-similarity. So g sub lambda has more properties, because let's look at our construction. So let me go. So our IFS is sitting inside this interval, and let's suppose that we know the value of g sub lambda at some number u. So let's suppose that we're given g sub lambda. So we know nothing about what the set looks like. We just know that G sub lambda u looks like something. So this corresponds to some sort of cover in terms of ball of the radius 2 to the minus u. So these are 2 to the minus u balls. Okay, so because of self-similarity, well, I can take my set lambda, and I can find some map. Let's call it like some composition. Maybe like f sub I1 equals with f sub I n. So I can find a copy of lambda which sits inside each of these balls because of self-similarity. Self-similarity basically means that you can always find small copies of your set everywhere. So in particular, I can find a small copy inside each of these balls. So inside each of these places, I can find another kind of small copy of lambda rescaled by compositions of my similarity maps. And well, how big is lambda? Well, lambda is a set. We don't know too much about lambda at this point, but we know that the Hausdorff dimension of lambda is at least h, or the Hausdorff dimension of lambda is 8. So this is an h-dimensional set. So what that's saying is that, okay, well, whatever happens at level at scale 2 to the minus u, I have a whole bunch of family of balls. And inside each balls, I can put some h-dimensional set. So there's some set inside here, which is an h-dimensional set. In a uniform sense. So there's like a there's a reasonably big set inside each of these things. So maybe I draw the kind of corresponding 3 instead of this and so on. So what's that saying? Well, here, so this property said that, okay, every single ball was contained inside a one-dimensional set. So we got the upper one-dimensional property. Now we're saying that every single ball contains some subset which is h-dimensional. So that's the same as saying that it has to be lower h-elliptic. It's a lower bound of the Lipschitz constant. So the second property is that G sub lambda is lower h-elliptic. What do I mean by that? I mean that G sub lambda of u plus v is at least the value of u plus h times v. So we're not just increasing; we always have to have like a slope h gain. That's these two things make sense. So they're kind of like there's like two natural kind of properties that this function has to have. And it turns out that these are the only two obstructions. So somehow these are the only two properties that G sub lambda has. That we don't know about. In the following sense, so theorem. So G sub lambda is equal to is the smallest possible function satisfying these two conditions. It's the infimum over all functions f, such that f is at least G sub f, and f is lower h Lipschitz. And it's a branching function in the sense that it satisfies conditions 1 to 3, plus conditions 1, plus conditions 2. So basically, there's some list of rules. So we know that it has to be a branching function. We know that it has to be at least G sub f, and we know that it has to be lower h Lipschitz. And then otherwise, it's as small as possible. So basically, this is some function. So this is a function which takes as an input number h, and takes as an input this function G sub f, and spits out G sub lambda. So again, let me kind of sketch what this picture looks like.
But here f is not the same as
That's it.
the same.
Same f. Yep. It's a set of fixed points. It's a set of left endpoint subset. So I don't need any more information. I mean, now I need to know a lot of stuff about f. Right? I mean, I have all this information about f. I know the covering number in every single scale, basically up to some error term. Yeah, so all these are up to some like error terms which are negligible. Of course, there are like constants flying around absolutely everywhere. Okay. Yeah, so I think it's good to draw what this function is doing. It's a nice thing about the reason why the normalization, the branching function normalization is great, is because drawing Lipschitz functions is very easy. So let's start with our set f. Okay, so the branching function is an increasing, it's 0 and 0. So we have our graph. The branching function is 0 and 0, it's an increasing function, and it's the most malicious. So let's get some function. It looks like this, and then like this, and like this. This is the branching function. Okay. So what information do we know? So the branching function lives inside a cone. Maybe this cone is like this. So we have like two slopes. The slope here is the lower box dimension. The upper slope of the cone is the upper box dimension. It was called f. But the branching function is some Lipschitz function, increased Lipschitz function, which lives inside this cone formed by the lower box dimensions. And what are we saying? So we're saying that this is let's call this function g sub f. So this is the function g sub f. So we're saying that g sub lambda has to be bigger than g sub f. So we need to draw some function which is lower bounded by the function here, and which has slope of at least h everywhere. So maybe for the first bit, the slope is bigger than h, but then out here the slope is 0. Right? So now I need to continue with slope h until the function again, maybe that I go up some slope. So maybe here the slope is now slightly less than h. And so basically I just follow the function g sub f, except in the places where the slope of the g sub f is too small, in which case I increase that slope h. Because these are the only two constraints, right? I need to be lower bounded by g sub f, and I can never have slope which is too small. So this is the function g sub lambda. G sub lambda is this function formed by the equation. Yeah, and this somehow this captures all the information. This tells you everything which is going on. So that if you're given all this extra information about f, then in return you get all of this precise information about this. And sticking to the talk, I want to explain why does this give this bound. So how do we obtain this bound here, which is that this upper bound on lambda. Okay, so I want to prove. The proof. Sorry. Okay. So the first thing to do is to note that this function is. So we can consider this as an operator, right? Like this is an operator which takes as input a branching function and outputs a branching function. So this is just some function which is defined on the switches function. This is monotone in the sense that if I input a function which is uniformly lower bounded by another function, then the output will also be the output is monotone. If I start with a bigger function, then I'll always get a bigger function here. Okay, so this is monotone. So what do I do? So I'm given a set. So I'm given a bunch of numbers. So I'm given. Okay, so what's our input? So we're given the number h. We're given this lower cone. We're given this lower cone s with slope s and this lower cone with slope p. So this is a given gradient. So we know nothing about g sub f. We just know this information. So we start with h and we have some cone. The lower cone has slope s, and the upper cone has slope p. Okay, and the branching function lives somewhere inside this cone. But of course, this is like the best possible cone. So we know that there has to be some location where the branching function hits the cone. So it hits the cone somewhere. Because the lower box dimension is a limit, and the limit must be realized along some sequence, so we can find some location. I mean, not literally hit up to some error term, which is very small. But let's imagine that it literally hits. Okay, so this is some scale where the lower box dimension is realized, but we know nothing else about g sub f at this point. Or well, not quite nothing else. We know a few things, right? Well, we know that I erased it, but we know that it has to be an increasing function. Okay, so because it has to be an increasing function. I can't exceed this line. So g sub f must lie underneath this line because it's increasing. Right? So if I just draw a straight line, that changes. And also, because the slope has to be at most 1, if I draw a slope from here of slope 1, this line. Well, then it has to also be underneath this line. Right? So this function is an upper bound. So g sub f is bounded above by this function f. Maybe I'll try to find a different way. So I have some function f. So we know nothing about g sub f. We just know that it has to lie underneath this. Okay. So because this function is monotone, that means that g sub lambda has to be bounded above by applying this function, which is just defined on bracket functions as an abstract sets, to the function f. Let's call that g. The g sub lambda has to be bounded above the new function g. So, and how do we obtain g? We obtain g by just applying this slope h operation to this upper bound. So here the slope is, let's say we follow the slope for some while here, but then now here the slope is 0, so we increase that slope h. This is slope h, and then now the slope is too big again. This slope is just 1, and we know that h is almost 1. So g sub lambda is smaller than g. But then if g sub lambda is smaller than g, well then there is another line we can draw here, which has slope, let's call it S prime. And S prime is this number. That's what this number is. It's a slope which you get just by doing a bit of some small calculation. Yeah, so basically, even though we know very little about the function g sub f, we can just use like general bounds plus the fact that, yeah, we can just use some general bounds plus some sort of like plus monotonicity of this function to get an alpha bound of f prime. And also we can see here why this is somehow, why this is sharp. Sort of like why every single value in between is also attainable. Because there's no reason that the function g sub f has to look like this y function. Well, it could be something just much smaller, right? So f prime is like we can guarantee it has to lie underneath f prime here. But that's all, right? Like it could be much smaller. Like instead of g sub f looking like this y line, it could look like this y line and then follow slope f for a very long time. In which case this number s prime would just be something totally different. So in particular, this is like you can use it. You can also use it to construct counterexamples in the sense that you just fix your favorite set f, which has some branching function which you cooked up to have some properties, and then you approximate f by some sequence set, and then you build an IFS using that sequence set with contraction ratios that are chosen in a way so that the Hausdorff is what you expect, and then you apply this theorem which says that you get the output that you expect, and then this will tell you the formula for it. All right, thank you.
Thank you, Alex. Questions? Local audience? Oh,
Have to ask packing dimension.
Same.
Okay.
Yeah. It's because f doesn't disappear at the first level, it appears at every single intermediate level.
Okay.
Everything is countably scalable. Even though f is like it's not it's a quite a heavy instruction. Like f is like the full tree somehow.
Okay.
Yeah.
I always hate to be that person who asks, so
Yeah.
for some people.
Yeah.
and our online audience, please ask a question and hopefully we will hear it.
Can you hear me?
Okay.
Maybe?
That's a
Can
bit.
you hear me? Maybe not.
Yes, we can hear you.
Ah, great. Hi, Alex, Sasha here. I was wondering whether you considered also Minkowski content. The function g looks very much like what you would do to prove, well, using a renewal theory that the Minkowski content would exist, for example, if something is a bit irregular. And I think you might be able to get something similar here in terms of a kind of a dichotomy of when.
Yeah, I mean, I'm lying a lot. Yeah, I'm lying a lot in the sense that there are like error terms which will make this impossible. At least our proof has like O of U, little O of U losses, or like logs of losses basically. And this is like not enough for Minkowski content. I think the situation should be so. I'm lying all over the place. So here's another place where I'm lying. So remember here when I said that if you look at some ball that you can find some like subset, right? Well, the problem is that the corresponding cylinder could be way bigger, right? So this is not actually true. It's only true on average. So there's also some losses there which are like fundamentally unavoidable. So there are things like this. So I don't think the proof idea would give Minkowski. I think Minkowski content just behaves very differently. This is my guess. But it's a very
Thank you.
good yeah. Yeah.
Any other questions from online audience, please? Higher dimension?
Well, so everything works in RD, everything works with conformal maps instead of similarity maps. But you could ask about like affine, like self-affine, then that's a disaster, but who knows? Yeah. But affine is a different world, even the finite case is not understood. Yeah.
Okay. And everything works for self-similar but for self-conformal?
Yeah, also works.
Also for self-conformal.
It is more technical. The proofs are like 3 times as long, but it's the same.
It is the same.
Yeah.
Okay. So any other questions from the online audience, please? We do not hear it. So thanks, Alex. It's very nice talk to you.
Sasha, I'm going to say Sasha. Is Sasha still there? Or I don't know how to talk to Sasha.
Yes, I am.
Oh, cool. Yeah. So there's a paper about Minkowski content. Maybe I remember reading 1 or 2 papers about Minkowski content, and in a lot of the cases where this function is non-trivial, the Minkowski content was just infinite, I think. Like, I think there were some conditions, like, I think I think it's unknown what the answer for Minkowski content is, but it's known that it's different. Basically.
Okay.
Yeah.
Right. I see.
Yeah. I maybe Mark Kesselbaumer did something like this. I can't remember who said.
Yeah, I've not really looked at with infinite IFAS and the entire question of Minkowski content, but also like correct gauge functions and positive and Hausdorff measure.
Yeah. I mean, yeah, you could ask for like better. Yeah, I mean, the asymptotics here are very, very loose. Yeah, just slower than you, but not linear, something but that's it.
Yeah. But I guess when you're up and lower diff, you can still say, well, the content does not exist, of course, because, well, the two notions are different.
Yeah.
So you can at least say something in that direction. Then I guess you would just need higher order terms when you're close to one of the two. And maybe having an argument where some of the contraction ratios are different, or you are in a strictly conformal setting, that might already be enough to say that there's enough mixing, geometrically speaking, that the content might exist. But okay. Yeah, I don't know.
Yeah. Anyway, yeah.
Okay. Thank you.